The following is the video solution from JSDT Solutions. Question 7.1 says, given f of x is equal to 3 over x, we need to determine f prime of x from first principles. Okay, so to find f prime of x, remember that the equation looks like this. Okay, it's to find the gradient of this function. So we clearly still have to find the f of x plus h since we have f of x. Okay, but we'll just find it while substituting. So this is equal to the limit as h approaches 0. And so f of x plus h, to find this, wherever we see x, we just replace it with x plus h. So this now becomes 3 over, we have x, so that's x plus h, minus f of x, which is 3 over x. And all of this is divided by h. Okay, so we have a fraction in the numerator that we have to simplify. Do you see that in this fraction, the denominator here is x plus h, and here the denominator is x. So we're going to have to make the denominators the same so that we can actually subtract them, because in order to add or subtract fractions, your denominators need to be the same. Okay, so they need to be equivalent fractions. So the limit as h approaches 0, we're going to make the denominators the same, and we can do this by finding the LCD, or the lowest common denominator. And really all we're doing is we're trying to make the denominators the same. So we look at this denominator and say, how can we make them exactly the same? Well, you can do that on this side by multiplying this denominator by x and multiplying this denominator by x plus h. Okay, but remember what you do on the bottom, you must do on the top. So we're also going to multiply this numerator by x and this numerator by x plus h. And so that's why our common denominator is x times x plus h. And then our numerator is simply going to be 3x because they multiply. And on top here, we'll have minus 3 multiplied by x plus h. When using the LCD method, it's just a simplified version of this, okay? Because with the LCD method, you just think about what the LCD is going to be and then look at each fraction and ask yourself, what did you multiply to that denominator so that you can get that denominator to look like this? In this case, we multiplied this denominator by x, therefore we must multiply the numerator by x as well, and vice versa. And this also applies to the second fraction. Okay, so this is what we have, and we can just go ahead and simplify. But remember that we're still dividing by h. So here's how I'm going to do this. Because this is now a fraction, I'll just say we're dividing by h. And we can also rewrite h as a fraction by rewriting it as h over 1. So now this is equal to, we have the limit as h approaches 0, and now this is 3x, and this distributes in minus 3x and minus 3h all over. Now with this, I'm going to keep this as it is because I can already see we have an h here, which we can take out as a common factor. And here we have an h, but we're dividing by h. So when we use tip and times, this is going to become multiplied by 1 over h. And you see now we're going to have an h in the denominator that is going to cancel with that numerator of h. So always think ahead of time when working with these problems. So now we have here x times x plus h is equal to, and this is the limit as h approaches 0. And so the 3x and 3x cancel. So now we have negative 3h, and that h is going to cancel with this denominator. Now you see everything that is here, right? It's just negative 3h left. It multiplies with this numerator of 1. And then the denominator multiplies with this denominator of h. So we have hx, we can call it hx, multiplied by x plus h. And now our numerator of h and our denominator of h cancel. And f prime of x currently is the limit as h approaches 0. And all we're left with is negative 3 over x multiplied by x plus h. And now it's safe to substitute 0 in place of h because it will not cause our expression to become undefined. Okay, so this is equal to, so we'll just say f prime of x, and let's get substituting at this point. So negative 3 over x multiplied by x plus, and now this is 0. Okay, and finally, f prime of x is equal to negative 3 over, we know that that just gives us x because it's plus 0. X times x is x squared. And that is our answer. And moving on to the next question. Question 7.2 says 7.2.1, we have to derive the following expression. So how do we derive this function? Well, there's a lot of things that is wrong with it right now. First, we can see that we still have surds, okay? The surds include x. So they need to be written like the way this one is written, okay? So to the power of a rational exponent. And so we're going to do that there. But we also have these two values subtracting, and they're over something in the denominator, which is also a surd. Okay, so we need to fix that. So what we can do is just first of all break them open by rewriting them under a separate denominator, okay, under this denominator each. So we're going to say that this is, we're not deriving yet, so we'll continue writing dx, and we have, and let's just rewrite this as x raised to the power of, so a rational exponent. You're going to say the inside exponent over the outside exponent. And so that is 2 over 3. And then that goes over on its own. So I'm separating those, okay, to let them have that denominator each. So that is going to be x to the power of. And the exponent here is an invisible 1 on the x. And then this is a square root. So this is a 2. So it's inside exponent over outside exponent, meaning 1 over 2. And then this is minus x raised to the power of negative 3 over 2 over x raised to the power of 1 over 2 as well, because it also gets that denominator. Okay, so you know that the way we were able to add them together is because they had the same denominator, and that's why we're able to separate it like that. Okay, if you have 2 plus 5 over 3, you can rewrite this as 2 over 3 plus 5 over 3. Okay, that would just be to expand it. And then let's go ahead and simplify so we can still derive. So these have the same base and they're dividing. So it means that the exponents are going to subtract. So this is x raised to the power of 2 over 3 minus 1 over 2. What is 2 over 3 minus 1 over 2? Well, the denominators are 3 and 2. You can just use a calculator, but we can just multiply here by 2 in the numerator and denominator. And so that's 4 over 6. And then here by 3, so that's 3 over 6. And so 4 minus 3 is 1. So we have 1 over 6 there. So this will become 1 over 6. And then we have minus, and then same thing here. Your exponents are going to subtract because we are dividing by values with the same base. So x raised to the power of negative 3 over 2 minus 1 over 2. So that's going to be negative 4 over 2. But negative 4 divided by 2 is negative 2. Okay, and now we are ready to derive. So we can say is equal to, and we'll use the rules of differentiation. So it's the coefficient multiplied by the exponent, which is 1 over 6. And then we have x raised to the power of exponent minus 1. We can rewrite this one as 6 over 6. 1 minus 6 is negative 5. So this is negative 5 over 6. That's what we get there. And then coefficient times exponent, that's a negative 1 we have there, invisible 1, multiplied by negative 2, and that's positive 2. And we have x raised to the power of exponent minus 1. Negative 2 minus 1 is negative 3. And there we go. This is our expression derived using the rules of differentiation. Moving on to the next question. Question 7.2.2 says we need to determine dy over dx if we have this equation. Okay, so let's go ahead and first make y the subject. Okay, so let's rewrite our equation. We have xy minus y equals x squared minus 1. And we can just take out a common factor of y here first. So y comes out, and we're left with in the first term x, and in the second term, it's just negative y. So it is negative 1. You can always say this term, okay, negative y divided by that common factor. Okay, so this is what we have, and we have x squared minus 1. And then to get y on its own so we can determine dy over dx, we're going to divide both hand sides of this equation by x minus 1. Okay, so we have y equals x squared minus 1 over x minus 1. Now, do you see that in the numerator and denominator, okay, we're going to have common factors because this can be factorized using difference of two squares. So y equals, and we're going to open up two brackets. So this is going to be x minus 1 times x plus 1 all over x minus 1. And so these two would cancel, they simplify, and so therefore y is equal to x plus 1. And now to differentiate this, okay, in respect to x, we're going to say, okay, to find dy over dx, now we're ready to derive. So we'll say dy over dx is finally equal to, and using the rules of differentiation, coefficient times exponent, so that's 1 times 1, which stays 1. And so we have x raised to the power of that exponent of 1 minus 1 gives you 0. And anything to the power of 0 is equal to 1. And you know that if you derive a constant, it gives you 0, okay? Because a constant is really just like a line. Y is equal to 1. This is a horizontal line, and the gradient of a horizontal line is equal to 0, and that's why it becomes 0. Okay, so dy over dx is equal to 1, and that is our answer. Moving on to the next question. Question 7.3 says, the gradient of the tangent to the function represented by f of x is equal to ax cubed plus bx squared. So we have a cubic function. At the point 1 and 5 is 12. And 7.3.1 says we need to show that a is equal to 2 and b is equal to 3. Okay, so let's visualize this. We have a cubic function. And just because they said a is equal to 2, we'll just go ahead and show them that this is the cubic function where a is greater than 0. Okay, the coefficient of x cubed. And this cubic function has a tangent running to it. Okay, so we have a tangent to this cubic function, and they tell us where this tangent, okay, intersects this graph. So this tangent is at 1 and 5. And this tangent has a gradient of 12. Okay, the gradient of the tangent to the function represented by this at this point has a gradient of 12. And how do we find a and b? So we have two variables missing, but they only gave us this information, this point, and telling us that the gradient is 12. Well, this point has now become powerful because we now know the gradient at that point. And so we can use this information twice. And this is how we can use it. And the reason I'm emphasizing that we can use it twice is because we're looking for two variables. In order to find two variables, you need two pieces of information that can help you form two equations, really. Okay, and this is how we're going to form these equations, despite two things being missing. So this is our function, and we can use this point first as a point having a gradient. Okay, and this is how we're going to do that. Because we know that the gradient at this point is 12, let's find the gradient of this function. So to find the gradient of this function, we derive it. And so this is f prime of x is equal to coefficient times exponent. So that gives us 3ax, exponent minus 1 is 2. Same thing over here. Coefficient times exponent is positive 2bx, exponent minus 1 is 1, and we don't have to rewrite that. So this is the general gradient of this function at any point. But they specifically told us the gradient of this function at the point where x is equal to 1. That gradient is 12. So here's what we're going to do. We'll say that we'll find f prime of 1, and we know what that gradient is. So long we're just substituting that x value of 1. We're saying the gradient of this function at the point where x is equal to 1 is, and we're just rewriting and substituting. And this is all squared plus 2b times 1. And the gradient of this function, okay, where x is equal to 1 is specifically equal to 12. So we'll say 12 is equal to, and we have 1 squared, which is 1 times 3. So this stays 3a, and then that stays 2b. Okay, great. We have our first equation. So we have used this information once. And now the second way we can use this piece of information that they've given us is like this. We've used this point as a point which we know the gradient of, and now we're going to use it as an actual point. So we'll use it as an x and a y value. So on this function, there lies a point 1 and 5. So in place of x and y, we'll substitute 1 and 5. So this is going to be in place of y, f of x, we say 5 equals a times, and in place of x, we say 1 all cubed plus b times 1 all squared. And we just simplify this. So 5 equals, and we have 1 cubed, which is 1. So it's just a plus b. Okay. Now you can see that with this equation, it's easier to make something the subject. So we can do that. Now, at this point, you can decide how you want to solve for this simultaneous equation, because that's what it is. It's a simultaneous equation. Okay. So I'm just going to solve for this by making something the subject here. Okay. So I'll go ahead and make a the subject. So leave a on this side, and we're going to transpose b. So this is 5 minus b. And now I'll go ahead and call this my equation 1, and this one my equation 2. So we're going to substitute equation 1 into equation 2 so that we can solve for b first. So this is now 12 is equal to, and wherever you see a in equation 2, you substitute 5 minus b. So 12 is equal to 3, and then there's a. So that's 5 minus b plus 2b. Okay, and let's simplify further. So 12 is equal to, and we'll distribute. This is 15, and then minus 3b plus 2b, and these would add. So 2b minus 3b is negative b. So this is negative b, but you could just transpose this from the right to the left-hand side. So it becomes positive b is equal to, we still have the 15 on the right-hand side, and we can take this 12 over, so it becomes negative. And so 15 minus 12, we know that that is equal to 3. So therefore, b equals 3. And we've solved for b. Okay, just like they said it would be. Now to find a, you can just take this and substitute it into the equation that had a as a subject, which is equation 1. So a is equal to 5 minus b, but we know that b is 3. So therefore, a is equal to 2. And there we go. We've solved for a and b. Moving on to the next question. Question 7.3.2 says, calculate the coordinates of the points on the curve where the tangent to the curve is parallel to the x-axis. Yeah, okay, so this is one of those long journey to a simple answer. The whole thing about this, right, is just in the wording of how they phrased it. So let's just think about what they're referring to. So they want us to calculate the coordinates, okay, of the points on the curve where the tangent to the curve is parallel to the x-axis. So on this curve, where do we have the tangents being parallel to the x-axis? We know the x-axis looks like this. So where can you ever have tangents parallel to this x-axis? Well, think about that. If it's parallel to the x-axis, we can even just like carry this line parallel to the x-axis and move it all through. You see, it can never be a tangent anywhere here. You can see how it just cuts through here and cuts through there, okay? But the only way it can be a tangent to this curve is right there at the turning point. So at that turning point, it can also be a tangent to this curve, okay, at this turning point. So it's a tangent at this point over here. So this is a fancy way of them asking you to find the turning points of this function. So let's go ahead and find them. So this is f of x is equal to, and let's just rewrite our expression knowing a and b. So this is now 2x cubed and positive 3x squared. And let's find the turning points. How do we find the turning points of a cubic function? We have to remember that really in any curve, we have to keep in mind that at the turning point, this is where a tangent to this curve, or the gradient really, at this point is equal to 0. So it means that the tangent to this curve's gradient is equal to 0 at this point. Okay, so, and it's also equal to 0 there. So we'll find the gradient of this function. So f prime of x equals, and that's going to be 6x squared plus 6x. And when we find the general gradient, we're going to find out where exactly is that gradient equal to 0. So we're making that equal to 0. So 6x squared plus 6x. Let's go ahead and solve for x to find out where this happens. So you can see that we have 6x in common. So we can just take 6x out as a common factor and we're left with x. And in the second term, you'll just be left with, so 6x divided by 6x is positive 1. Okay, and I'll just put the 0 on the right-hand side. So something multiplied by another thing gives you 0. It's either the first factor is equal to 0 or the second is equal to 0. Therefore, x is either equal to 0 or x is equal to negative 1. So these are the x values of those turning points. The x values where we have the gradient of the tangent being equal to 0. But they want the coordinates, the full coordinates. So let's go ahead and find them. So we're going to have to take the original function and we'll take those x values and we need to find their y values. Now with the 0, that one is quite simple. You see that if you substitute 0 here, it's also going to give you 0. Okay, so in this case, this is an x and a y intercept at the origin. So we know that f of 0 equals 0. Okay, and then if we substitute that negative 1 in, we're going to get 2 times negative 1 cubed plus 3 times negative 1 squared. And we know that if you square a negative value, it becomes positive. So that's just going to stay 3. But this one is going to stay negative because it's cubed. So 2 times negative 1 is negative 2. And so 3 minus 2 is 1. Okay, so those points are 0 and 0. And the second point is negative 1 and 1. Okay, and that is our answer. And that is it for question 7.